All right, so we're back to chapter one again. We're not quite done with it. It's a very long chapter, as you know. And so I'd like to take a step back and pick it up again with polynomial functions. I know we did this the other day, or at least we started it, but I just want to quickly review this before we go on to what's next. So you might recall that a polynomial is a function that has typically many different terms. And you can see that what characterizes it is that we have powers of x that can go from 1 up to any number n. And each one of these may or may not have a coefficient, an, n1 is 1, etc. And this last term, a0, is a constant. Now, the important detail here is that in order to qualify as a polynomial, n must be non-negative, which means it could be 0, or it could be 1, 2, 3, etc. It can't be negative, and it can't be a fraction. If it is, then this is a different kind of function altogether. So we have to make sure that we recognize a polynomial when we see it. And there's many different polynomials that we're very familiar with. For example, a linear function is actually a polynomial of what we call degree 1. The word degree refers to the fact that the exponent is 1, or the highest exponent is 1, is what I should say. And so, of course, that is often written as y equals mx plus b. You can see that it also could be written as f of x equals a1x plus a0, and because it means the same thing. Quadratic function is simply a polynomial of degree 2 because the highest exponent is 2. And here, the only constraint we have is that a, the coefficient of x squared, cannot be 0. Okay, it could be anything else. And by the way, don't forget the restrictions on a polynomial are the exponents, not the coefficients. The coefficients can be anything. Those exponents have to be non-negative integers. So the only reason why a can't be 0 is because then this would reduce to a linear function. And then finally, well, not finally, but this is the only other one that we tend to see in practice with applied applications such as engineering or physics or economics. We don't often run into polynomials with higher degrees. Here we have a cubic function, and that simply means that the highest exponent is 3. Now, I just want to point out that we don't have to have the x squared term or the cx or the d. It literally could just be y equals x cubed, and it still qualifies as a third degree polynomial. Okay, the only thing we must have here for it to qualify as a cubic function is the x cubed. The rest of these terms are optional. Now, here's a quick check of some functions that may or may not be polynomials. And so the first one clearly is, because the only two exponents we have here are both clearly non-negative integers, 2 and 4. We have a constant as well, but this is what we're concerned about. These exponents cannot be negative. They cannot be fractions. Now, the coefficients can be negative. That's not a problem. Number 2 is also a polynomial because the exponent here is 1. There's an implicit 1 here. And here the exponent is 3. And of course, 1 and 3 are both non-negative integers. But the third one is not a polynomial. You can see why. Most of the terms are okay, but then all of a sudden we have this negative 2 here, and that rules this out as being a polynomial. Okay, so that's all that it takes. One of the terms has an exponent, which is not a non-negative integer, and that means it is no longer a polynomial. Here's another example I made up last time. You can see that, again, all the terms but one are fine. The one that's not fine is this radical x, because if you recall, radical x is the same thing as x to the 1/2 power, and obviously 1/2 is not an integer. Therefore, this is not a polynomial. Now, here's another couple of examples. This one is a polynomial. But this is just the explanation for the same ones. Okay. Sorry, let's jump ahead. Now, here's some terminology. The degree of a polynomial is the highest exponent that we find in that equation. For example, here, this one is said to be of degree 4. This one is of degree 7. And this one is of degree 5. So what that means then is very simply a linear function is a polynomial of degree 1. Okay. A quadratic equation or function is a polynomial of degree 2. And then finally, a cubic function is a polynomial of degree 3. Now, by the way, there are names for the higher order polynomials. Like, for example, the 4th degree is quartic. If you're really interested, you can go to Wikipedia. And, you can, if you search carefully, names of higher order polynomials. There we go. So this is what I was saying. 4 is quartic. 5 is quintic. 6 is sextic, et cetera, et cetera. So like I said, they all have names. But in practice, you can see, like, for example, 7 is septic. That's kind of a strange one. 8 is octic, 9 is nonic, and finally 10 is decic. You're not going to hear those very often. Like I said, for practical applications, most of the time the functions you run into are either 1st, 2nd, or 3rd degree. Oh, also, by the way, a constant is considered to be a polynomial of degree 0. Okay, if you want to be super technical about it, because what is a constant? A constant is a number that you could think of as being multiplied by x to the 0 power, because x to the 0 power is just 1. So that actually qualifies as a very special polynomial, a polynomial of degree 0. Okay, now the leading coefficient is simply the coefficient of the term with the highest exponent. So here, for example, and by the way, this is one of the advantages of writing out polynomials in descending order of exponent. We all know that this is how it's done in practice. You always put the highest exponents first, you work your way down to the smaller exponents and then the constant. Part of the reason for that is so that it's easy to identify, for example, the leading coefficient. Here it's just 5 and here it's 9. And it just makes sense. It's like reading from left to right. I mean, it's just something that you get used to. The highest orders comes first, and then you work your way down to the constants. This one, of course, then has a leading coefficient of -8. All right, so up to this point, we've been looking at different kinds of polynomials. Now we're going to focus our attention again on quadratic functions. And again, now that we know, a quadratic function is simply a polynomial of degree 2. This is what it looks like. The coefficients. By the way, if you noticed, when we wrote this originally, in the most general possible form, we were writing it like this. But these a's are just constants anyway, so it really doesn't make any difference what we call these coefficients. It amounts to the same thing. They're all just constants. And once again, the only constraint here is that a cannot be 0, because otherwise we just end up with a linear function. And certainly b can't be 0 either. Well, b can be 0 if a is not 0. You can have a function like x squared minus 2, and that still qualifies as a quadratic function. And of course, we know that a quadratic function has a graph, which is referred to as a parabola. Okay, we know that a parabola is symmetrical and it is U-shaped. So let me just draw a quick example. Our simplest case. And this one is symmetrical about the vertical or y-axis, meaning that the left-hand side and the right-hand side are identical to each other. And of course, it does look like a big U. It's not a very formal way of describing this. There's probably a formal name for this somewhere, but we can just think of it as U-shaped because we know that it continues to rise forever. And so this is a parabola, and there's only 2 basic types of parabolas based on the coefficient of the x squared. If a is positive, the parabola faces up or opens upward. Like this one, for example, a is 3, 3 is positive, therefore this one faces up. In fact, some people, you hear this sometimes, they say that it holds water, a very imprecise, informal way of describing it. But yes, if you, it's like an upside down umbrella, basically. And if you left it out in the rain, it's going to get filled with water. On the other hand, if A is negative, then we have the opposite case. The parabola opens downward. Some people would say that it does not hold water. All right, again, a very informal way of describing this. And the reason why it does this is because A is negative. Now, if A is not zero at all, it's neither positive nor negative. I'm sorry, if it is zero, if it is zero, then it's no longer a parabola. And you would just have a straight line. Okay, so we don't have to worry about that case. Okay, now, what are the characteristics of a parabola? Well, we have four things that uniquely characterize it. We'll describe in a minute, is the vertex, the axis of symmetry, the zeros or solutions, and finally the y-intercept. Now, we've already looked into solving a quadratic equation. The two basic ways we do this, we can find them typically with either factoring or the quadratic formula. Which we're all very familiar with. The axis of symmetry, we'll get to that in a minute. The y-intercept simply means where does it cross the vertical axis. So just like a straight line has a vertical intercept, so does a parabola. Okay, there'll be a single unique point. If the function, the parabola is facing up, this will be the smallest point or the minimum point where y reaches its smallest possible value. And if it's the other way around, well, then you'll see that clearly this is what we will call the maximum point. Y cannot get any larger than that. So that forms the boundary, the upper boundary for the range, whereas over in the right, it's the lower boundary. So the range, whatever this point is, the range starts here. I mean, this is the end. Let's say this is the point HK. That means the range is everything from negative infinity up to including the K. Whereas over here, so in other words, it's everything from K down to negative infinity. Whereas here it's the other way around. That's the starting point, and it goes up to infinity. Okay. So the vertex just means either the minimum or maximum point on the function. Okay, so in other words, each of these two are considered to be a vertex. It could be either the minimum or maximum. And I just want to quickly throw this in here. The plural of vertex is vertices. Okay, just in case you run into that. So in other words, vertices is this plural, vertex is the singular. So as I just mentioned, if A is positive, the parabola opens upward, and the vertex is the minimum point on that function. Minimum in the sense that this is the smallest value of y. And if it's not, in this case, this would be the vertex. This is the maximum point. Okay. Now, how do we find this point? Well, first things first, as is so often the case, there's alternative ways of expressing a function. We know that there's at least two different ways of expressing a straight line or a linear function. The same thing is true here for a quadratic function. This is the one we know the best, but this one also will give us the same information in a slightly different way. It's written this way so that it's clear just by looking at it that H comma K is the vertex. In other words, those are the XY coordinates of the function's minimum or maximum point. So let's take a look at an example where we take a quadratic function and solve for its vertex. So here it is, 2x squared minus 6x plus 7. So clearly A is 2, B is -6, C is 7. Now on the next slide, I have the graph. You know what I'm going to do? Let's go to Symbolab. I mean, this is okay, but it's not as maybe precise as it could be. You know, Excel is a great package, but it may not always be the best choice for graphing math. Y equals 2x squared minus 6x plus 7. Now, the other good thing about Symbolab is it will actually identify the vertex for us, even if we don't ask for it. Now, see, this is what I mean. You can't really tell from this Excel graph that it isn't actually touching the horizontal axis. It's very difficult to see it properly. You can see here, 3 halves, 5 halves. They're calling it the global minimum. And what that means is that this 5 halves, the range of this function starts at 5 halves and goes up to positive infinity. This point is the vertex. Although they're calling it the global minimum, it is the vertex. And in fact, you can ask Symbolab to tell you what the vertex is. But of course, they have changed the interface. It used to be right down here somewhere. You know what? Let's just see if this works. Yeah, I guess they're trying to make it so you just type the word. You can tell because it's in italics that maybe that's one of its keywords. But anyway, this is the vertex. Now finding it, well, I'll show you in a second how we're doing this, but it's exactly what they're telling you here. What you're going to do is rewrite it in this form. How do you find H and K? Well, based on the original way that the quadratic equation is written. And here's our vertex. H is equal to minus B over 2A. So for the equation that we're looking at now, if y equals 2x squared minus 6x plus 7, it means that A is 2, B is -6, C is 7, H is negative B over 2A. Okay, so this is going to leave us with 6/4 or 3 halves. So that's the x coordinate of the vertex. Now, as you can probably imagine, to get the y coordinate, what we have to do is find the original function where x equals 3 halves. Okay, so in other words, let's again write this down. Let me write it down as f of x this time because I want to make it clear that we're evaluating this. That's okay. So 2 times 6/4 minus 18 halves. Ooh, I just want to make sure I didn't make a mistake here. Nope, I sure did make a mistake right here. I knew something wasn't right. Hold on 1 second. Yeah, right there. All right. You were probably yelling at the screen when you saw that, saying, what's wrong with you? Okay. There we go. Now we're good. Okay, so HK equals 3/2, comma 5/2. And that's what a symbol F. So, okay. Yeah, they're showing the exact same steps. So you could write this more generally as H is negative b over 2a. Think of k as f of h. And so that's your vertex. Or what you could even do is just write and you're done. So that's your vertex. Okay. Now, as far as that format goes, a x minus h squared, let's go back and grab it right here, plus k. There we go. So that means in this case, we have 2 x minus 3/2 squared plus 5/2. So this equation and this one are the same parabola. They're just written a little differently. In the second case, it's written so that you can see the vertex right away. In the first case, what you're seeing is, of course, the coordinates, or coefficients rather, but either one of these could be useful depending on what you're trying to do. Now, what we also are going to consider here is this notion of the axis of symmetry. So whenever you draw a parabola, whether it's facing up or down, and whether, let's say it looks like this. Here's your minimum point. This is your vertex. If you were to describe a line through that point, you'll see that the function is symmetrical with respect to that line. Okay, so this is the line x equals h. So this is our axis of symmetry. It's that simple. In other words, a vertical line has an equation x equals some constant or other. That constant is the x coordinate of the vertex. So this is my axis of symmetry. This line, vertical line, that cuts through the vertex. Okay, so that's easy. Once you have the vertex, it's simple to find the axis of symmetry. So like in this case, the axis of symmetry would just be x equals 3/2. Okay, so remember, we found that we have for the vertex, that happen to be 3/2, that is the axis of symmetry. And that's all there is to it. So I already had done this in Symbolab. You can see that's the same parabola we've been looking at. The purple line is the axis of symmetry. Okay, and as x equals 3/2, we're calling that the vertex is simply 3/2, 5/2. This purple line is the axis of symmetry. Because you can clearly see that the two sides are mirror images of each other. And so that's what this is all about. Okay. And then finally, yeah, the quadratic formula. This is one way we can find the solutions. We mentioned this earlier. The solutions can be found either with the quadratic formula or else factoring. Although factoring really only works well when it's a very simple function, especially when a is equal to 1. In other words, you just have x squared. You don't have like 3x squared or 7x squared. Then it gets very messy. But all the time, no matter what you're doing, the quadratic formula works. Even though it could take a little longer than factoring, it always gives you a solution. Whereas factoring, if the solutions are very complicated, factoring could really be a nightmare. So I always recommend that people you just use the quadratic formula. It's something that you've known about for a long time. You might as well continue to use it. Turns out, interestingly enough, the axis of symmetry, as you can probably guess, the solutions, remember, or zeros, are where it crosses the axis. Well, it turns out the axis of symmetry is simply the average of those 2 points. It can't be any other way because the symmetry ensures that we'll have the same distance between the axis of symmetry and the 2 solutions. So that's why it has to be in the middle. Otherwise, it's not symmetrical and then no longer should be called the axis of symmetry. Oh, here we go. Here's a quick example. Maybe we could use a little practice here with a quadratic equation, a formula rather. So here, of course, there's an implied 1 for A. B is -3. C is -4. So using this quadratic formula, we plug everything in. And now, of course, the biggest challenge here is to not mess up the negatives. Okay, it's too easy. -3 is +3. Here we have 9, not -16, but +16, which of course is 25. So we have +3 plus or minus square root of 25/2, 3 plus or minus 5/2. Now this plus and minus means you have minus and plus. There's no reason why it has to be minus and then plus. It just seems like most books you do it this way. I guess it's just something that mathematicians decided, let's do negative first and then positive second. That's what we're used to. Let's stick with it. And you end up with -2/2 or -1. In the second case, you have 8/2, which is 4. Now, what that means is that when you take this function, x squared minus 3x minus 4, and the solutions are -1 and 4. That means that when you draw the graph, the first solution is -1. So that means the intercept section here is at the point -1, 0. Over here, you're going to have 0.4, 0. The y is just 0 because we're on the axis. This is the solution right here. The actual solutions are -1 and 4. What that means then is that f of -1 would just be 0. And the same thing would hold for 4. (16 minus 12 minus 4 is just 0. Perfect. All right, so now here a similar one. X squared minus 6x plus 8. So that means a is +1, b is -6, c is 8. We're looking for 2 points, whatever they are, where it crosses. I didn't draw that very well. And so we throw in the numbers and being careful. Now, of course, this first term is 6. We have 36 minus 32. So 6 plus or minus square root of 4 over 2, or 6 plus or minus 2 over 2. When you split that up into 2 terms, you're going to have 4 halves and 8 halves, which ends up giving us 2/4. Now, that means that both of these are on the right side here. But eventually the curve will continue to rise forever, and it will cover the entire real number line. But it just so happens that it crosses the horizontal axis at 2 different positive points, 2, 0 and 4, 0. Now, here's an interesting application of this. You wouldn't think it would work here, but a carpenter is building a rectangular picnic table. Due to space restrictions, the length must be 2 feet more than the width. Let's quickly review. So let's just say x is the width and x plus 2 is the length. Now, they're also telling us that the area must be 35 square feet. So whatever the length is x plus 2 times the width is 35. So what we're trying to do is figure out the dimensions of this table that we need to build. Now, if you notice, we're not trying to minimize or maximize anything. We're not trying to figure out the cheapest way of doing this, but we're just trying to figure out what dimensions would satisfy these requirements. So how would we do this? Well, it may not be obvious, but if you multiply this out, x plus 2 equals 35. By distributing x across x plus n2, subtract the 35, and we have ourselves a quadratic formula. Okay. A is 1, B is 2, C is -35. So we plug in everything. So we have 4 plus 140. And of course, the square root of 144 is just 12. So we have I'll repeat that here. Now, both of these are solutions of the quadratic formula, but since we're talking about width and length, clearly we can discard the -7 and we can just go with x equals 5. So if you recall, with the length of 7, and we have a width of x, which is 5. So that means the area, oh yeah, there it is, 35. So we are able to show that we have satisfied both requirements. The area is 35 and the length is 2 greater than the width. These are the only two numbers. These are the only dimensions that satisfy both restrictions. Okay. So -7, forget it. We can't have a width of -7. That will put us in another dimension, I guess. So here we're just going to focus on the first quadrant, and we end up with a solution of 5. Interesting. Now, the intercept, where is that? Right there. We can think of it as xy. The xy coordinates where y is 0. So you can think of this as x comma 0. Oh, sorry, 0 comma x. Because all along the vertical axis, x is equal to 0. So all you're doing is solving for f of 0. It's really that simple. If you notice, it reduces just to the constant. Okay, so as soon as you see a quadratic equation, you can immediately figure out what the intercept is by looking at the constant. So if you had y equals 3x squared plus 4x plus 7, that means that the y-intercept is 7, or you can think of it as the point 0 comma 7 is where it has its minimum value. Or not the minimum value necessarily, but where it crosses the axis. All right, now you probably are anticipating what's coming next. We need to formally define the domain and range of a quadratic function. Well, the domain is easy. It's just the real number line, okay? Because again, no matter whether a is positive or negative, eventually the function will reach every one of these real numbers. In other words, x is defined for every single x is defined for this function. And the same thing is true when a is negative. Okay, there's no value of x that can cause division by 0 or for there to be a complex solution. The range is the tricky part, but we mentioned this several times. This is, recognize this is k. So for this case, this is the point. That's our, oops, I didn't draw that well. That's our minimum point. So the range would be everything from this point up to, color it in basically. That's the range. So we're going to think of it as everything from k up to infinity, or you can replace that k with f of negative b over 2a. If a is negative, that means it's the maximum point that we're looking at. And that means the range, you can think of it as everything from negative infinity up to k, including the k. And k itself, remember, is f of negative b over 2a. It is simply the coordinate, the y coordinate of the vertex. So in other words, the range depends. It depends on the signs of A, B, and C, or A and B at least. All right, so I think it's time for an example. So as always, why don't we go to Symbolab and draw it? Minus 5x squared. No wonder it won't let me. I was in the wrong place. Now this one will be facing down. It will not hold water. Minus 5x squared plus 9x minus 1. Ooh, that's a tricky one. 9/10, 61 over 20. So what that means then, now, by the way, where did that come from? That means oh, sorry, that's not right. A is, let me write this down up here somewhere. A is minus 5. B is 9. C is negative 1. Therefore, H must be oh, 2 times minus 5. All right, the negatives cancel out. We end up with 9/10. K is f of 9/10, which we'll do in the next slide. All right, here we go. So we're solving for f of 9/10. So we have 81 over 100. So this 81 over 10, I'm going to turn that into 810 over 100. So this is 305. Yeah, that's it. That's as far as we can reduce it. So that means then that the range starts here and works its way down to negative infinity. So it's everything from negative infinity up to and including 61/20. Okay. So that's not too bad. All right. Just making a little note to myself. Okay. Now we have this interesting concept of power numbers or power functions. This is something where we have a constant A and a constant B. A is the coefficient, B is the exponent, and then we have X. It qualifies as a polynomial, assuming, of course, that B is a non-negative integer. If B is an even number, then this will be an even function. So let's remind ourselves what an even function is. Like x squared, odd function, negative f of negative x, and our example was x cubed. So what they're telling us is that if this exponent is even, then the entire function must be even, because f of negative x would be a negative x to the b, but because we know that b is even, these will be the same thing. In other words, we'll just get rid of the sign. Down here, if b is odd, then this is an odd function, because negative x to the b power will be negative. If x is positive, for example, negative x to the b power will be negative x to the b. And so that guarantees us that it'll be negative, odd rather, sorry, not odd. So here's an example. Let me show you this graph first. Now you can see it has that, it's sort of like that look that you get from cubic functions. It's a little flattened out. Now it's actually not a cubic function, but if you recall, anytime we have an odd exponent like that, we're going to call it an odd function. And an even exponent would be an even function. So it turns out this is actually 3x to the 7th power. And so again, even though it doesn't look exactly like, let's say, for example, x cubed, it has a similar look to it. It sort of rises, then it slows down, and then it falls. In fact, why don't we take a look at the graph of 3x to the 7th. Yeah, that's it. That is weird. In fact, just for the fun of it, why don't we see what it looks like with 9? To see if the shape changes at all. Now, based on the logic we've seen so far, this is clearly an odd function as well. And remember, too, we did say that an odd function means, yeah, okay, it is symmetrical between the first and third quadrants, or second and fourth, because it's symmetrical about the origin. And that's exactly what we're seeing here. The even ones are symmetrical between the first and second, or third and fourth quadrant. In other words, from left to right. And so this one, we can prove that f of negative x is -3, and this is equal to, and that means that this is odd. Okay. This one, on the other hand, as you can probably guess, is even, because the exponent is 6. And remember how that works. Even means, you can see why. When you have an even exponent, when you raise a negative number to an even exponent, it becomes positive. And so that's why this looks like this. And if you look at the graph, you'll see that the symmetry is from left to right, meaning that this is a mirror image of this one. So the first and second quadrants are mirror images of each other. And that's the characteristic of an even function. All right. Now, here's an interesting situation. We have what are called rational functions. And of course, when you see the word rational, in math at least, you notice right away the word ratio. In your daily life, the word rational doesn't necessarily have anything to do with ratios. Normally, somebody's considered to be rational, I guess, if they make sense when they talk. But here it just means you've got a function which is itself a function of, or a ratio of two other functions, which we'll call P and Q. Now, sometimes this can be very helpful. Now, here's a physics example. I couldn't think of any business example, so here's a physics example. We have a tank filling with water at the rate of 10 gallons per minute. At the same time, though, sugar is being poured into the tank at a rate of 1 pound per minute. We were given two starting values, 100 gallons of water and 5 pounds of sugar. So with this information, we will be able to tell what is the ratio of sugar to water or water to sugar, depending on which one we're interested in, at any point in the future. So what they're basically making here is something called a simple syrup, which is just water and sugar. It's often used in cooking. And so we're going to define the functions W of t for how much water is in the tank at time t. So remember, we did say that we started out with an initial amount of 100 gallons. Or you could think of that as W of 0. And then we were told that it increases at a rate of 10 gallons per minute. T is minutes, by the way. And here's the sugar. We started with 10. Think of that as S0. And then this is the rate. And this one, they don't have to be the same units, by the way. This is 1 pound per minute. That's why it's just T. So we're going to define a function called concentration, sugar concentration, which is simply the ratio of sugar to water. How much sugar is in this mixture relative to the amount of water? And, it may be that the company that's making the simple syrup has a particular ratio that they're aiming for. And so as they start pouring sugar and water in the tank, they need to know exactly at what point they've reached the correct ratio. Okay, let's say maybe it's 50-50, or, maybe they want 2/3 sugar and 1/3 water. Whatever they're aiming for, this is how they can find it. by creating this rational function, which is simply the ratio of sugar to water. And again, this is known as the concentration. We'll call it C of T. And once that's in place, we can find out how the concentration at any time t just by evaluating the function. Okay. So let me just copy this onto the next slide so we can remind ourselves what this function looks like. So initially, at time zero, that is, we put 0 for all the t's, and we end up with 5%. So in other words, initially when we started, we had, remember, 5 pounds of sugar and 100 gallons of water. So we had a 5% concentration. After 12 minutes, what level have we reached? Well, it's a simple matter of plugging in 12 for T. Turns out that the concentration ratio has gone from 5% up to 7.7%. So if you can imagine, if that's what we're aiming for, that tells us that we need to keep pouring sugar and water into the tank for 12 minutes before we reach our target. Now, later on, we'll see there are ways that we can choose the correct time for any concentration. In other words, given whatever the concentration is, 10, 12, whatever, instead of just guessing or trying different values of T, we can figure out precisely at what point we reach our target concentration. So there's a lot of potential uses for something like this. But for now, it's enough to note that this is simply known as a rational function because it is the ratio of two other functions. Okay, the only constraint, of course, is that we must not have 0 in the denominator. Other than that, anything goes. How about the domain of a rational function? Well, as you can imagine, what we need to do is avoid division by 0. So in a case like this, now what's interesting here is that if you notice, by looking at it carefully, the only number that would give us 0 in the denominator is -10. But because this is time and this is a real world application, well, t can't be 10. I'm sorry, it can't be -10. So we don't really have to worry about that. So in other words, because we're looking at time, the domain of this function is now technically everything from 0 up to infinity, including 0. Oh, by the way, let's graph this in Symbolab. And in terms of the graph, the only area that's relevant is the first quadrant because neither of these two variables can be negative. So all of our any results we're looking for would be with the understanding that we have to restrict ourselves to the first quadrant. Okay, I don't know what's going on. I've got too much stuff open as usual. Let me just open up Symbolab again. So what I'm looking for is a graph so we can better understand what this function is all about. Equals 5 plus t over 100 plus 10t. I don't know why he keeps doing that. All right, let's see what this looks like. There you go. Now, we already knew that t equals -10 was going to cause a problem, but this is interesting. According to what I'm seeing here, the concentration is never going to go above 10% either. And we'll see how to prove that later on in the course. Yeah. Yeah, don't worry, there's a way. We can do that, and we'll prove that 1/10, you notice how it's an actual asymptote. No matter how large T gets, this concentration cannot go beyond 10% because of the way the formula works. But for all practical purposes, then we're restricted to this range in here. Now here's another rational function, and this one is pretty straightforward. If you look at it carefully, you'll see that the denominator, x squared minus 9, if we set this equal to 0, we can factor this out or use the quadratic formula. These are the two values of x that would lead to division by 0. And therefore, the domain can be written in a very interesting way. Oops, sorry, this was supposed to be curved. Yeah, we're trying to leave out 3 and -3. So it's kind of complicated to write it with intervals in this case. But that's what it looks like. Everything except 3 and -3. All right. Now, finally, we have this last function when the exponent is a fraction like this, 1 over n, where n is itself a positive integer. Then we call it a root function. So this is, recognize this as, oh yes, these. So they're sometimes known as root functions. And I also want to point out that these are defined as even roots. These are odd roots. The main difference between the two is that on the left, the domain does not include any negative numbers. On the right, it does. So, for example, if I go back and look at the square root of x, oops, there we go. Yeah, you can see that the entire function is only within the first quadrant. No negatives. The domain and the range are everything from 0 up to infinity, including 0. But if I change that to a cube root, that's a very different story altogether. Yeah. So you got the first and the third quadrants because you can have negative y's and negative x's. Okay. So it has that sort of unique cubic look to it, but the domain and the range are both the entire real number line. All right. So, okay, this seems like a good stopping point. We're going to dive into exponential and logarithmic functions, very popular, very commonly used in real world applications, and very important, and also very interesting. So, okay, so we'll stop here and we'll carry on with the rest of this in the next lecture. and I'll see you next time.